Hello everyone, my name is Erfan Maleki. I am a third-year PhD student working at the Cloud Computing Lab at the University of Delaware. Today I will be presenting my paper entitled Mobility-Aware Computation Offloading in Edge Computing Using Prediction. So first, let's begin by talking about smart devices. A smart device is an electronic device, and generally they are connected to other devices or networks via different wireless protocols such as Bluetooth, Wi-Fi, 5G, for example. And they can operate together to some extent. And there are billions of interconnected devices that build the concept of Internet of Things. So smarter devices can be mobile or static. And several types of mobile smart devices are smartphones, smart vehicles, smart watches, smart tablets. Similarly, several notable types of static smart devices are smart doorbells, smart locks, for example. Our focus in this paper is specifically on mobile smart devices. However, our approach can easily be applied to all types of smart devices. So let's continue with smart mobile devices. The number of smart mobile devices is expected to increase to 16.8 billion in just 2023. So this directs to generating enormous amounts of data and brings a challenge for their computation requirements. So why is this a challenge? Because mobile devices are restricted by their weight, by their limited weight, limited size, limited battery life, and heat dissipation. This limitation imposes a severe constraint on their computational resources, such as processor speed, memory size, and disk capacity. And this limitation prevent the execution of highly computational intensive applications, such as speech recognition, natural language processing, and augmented reality. These applications are important to users because of their potential to augment the human cognition. So what is the solution for this challenge? Edge computing becomes a new promising approach to tackle this concern by bringing computation power closer to users at the edge of the network. At the same time, computation offloading to the edge provides mobile devices with higher capacity and with higher computational power. So edge computing addresses low response time requirement for users, manage their limited battery life, reduces internet bandwidth usage, and provides better data safety and privacy. However, the most challenging obstacle in delivering these benefits is users' spatio-temporal uncertainties originated from their mobility. Another challenge is the necessity for the migration of computation between edge entities, edge servers, cloudlets, to tackle this concern. But we know frequent migration leads to more data movement over the network and can degrade the performance for the applications. So let's continue talking about another property of edge computing, cloudlets. Edge computing consists of many cloudlets, which are like small data centers in the vicinity of mobile devices, and they are placed at the edge of the network. The total computational power of edge computing is distributed among these entities, and They can accept the computation of mobile devices, so they can mitigate the workload of mobile devices and enable them to run computation-intensive applications. What is existing work, their limitations, and what we can contribute? The existing work investigate the feasibility of mobility, but only for one user, one application. They don't have any guarantee on learning time, running time, or scalability. They model migration in other forms like cost instead of delay. They could improve smartness by having prediction from users' demands and location in the future. And they don't have any performance guarantee, like saying, okay, our approach in the worst case scenario can be 4 times or 5 times worse than the optimal solution. They lack heterogeneity, which means all cloudlets and applications and demands are same. They are assumed are same. They don't use real data, and they mostly rely on simulated data. In contrast, we contribute by having multi-user guarantee. We consider mobility for multiple users, not just one user. We have a combination of simulated data and real data. We don't just use simulated data. We have heterogeneous devices and cloudlets, and we ensure performance by having approximation algorithm. And then we use prediction approach to enhance the smartness of computation offloading problem. So now I want to talk about our system model. We show a set of M mobile application by notation U. We show set of M cloudlets by notation C. We assume we have a sequence of time slots represented by notation T. Specifications of application at time slot T is denoted by notation UIT. So here, XIT and YIT are coordinates of application at time slot T. And MDIT indicates the code and meta data of the application. IDIT is the size of intermediate data that is sent to a cloudlet in the middle of execution. And that omega IT is actually the computation requirement of application in terms of number of instructions or cycles. And PIT represents the processing speed requirement, and BIT is also bandwidth requirement of application. Similarly, for cloudlet, for example, cloudlet J, we have XJ and YJ, which are coordinates of cloudlet, and rho J and beta J indicate the total processing speed and total bandwidth of that cloudlet. We use Haversian formula to calculate the distance between application UI and cloudlet CJ because this formula is appropriate to calculate distance between coordinates in a geodetic format, which means in terms of coordinates, in terms of longitude and latitude. Here, RE is a large number, is the Earth's radius. And similarly, we use Haversian formula to calculate the distance between pair of cloudlets. Okay, our computation offloading problem is to find an assignment of all application to cloudlets, minimizing their turnaround time. Turnaround time is composed of offloading time, computation time, and migration time. We mathematically model this problem as an integer programming model, which is a highly constrained model and is NP hard. So we want to minimize the total turnaround time. The first term here calculates the offloading time. The second term calculates computation time. And the third term here is migration time. So as I said, we have multiple constraints, and constraint 1 guarantee each application is assigned to exactly 1 cloudlet at each time slot. The second constraints and third constraints ensure the total requested processing speed and bandwidth of the assigned applications to a cloudlet do not exceed the available processing speed and bandwidth of that cloudlet at each time slot. Fourth constraints ensure alpha ijk is 1 if uij t minus 1 and uik t are 1, which means application I migrates from cloudlet J to cloudlet K at time slot T. Otherwise, it is 0. Otherwise, it cannot migrate from cloudlet J to cloudlet K. And uijt and alpha ijkt are our decision variables and are binary. So as a general architecture, this figure shows the general architecture of our problem. So there are several mobile devices in the bottom layer, and they are mobile and can move across time slots. And each time they are assigned to a more suitable cloudlet. And in addition, cloudlets can access resources in the cloud if they don't have them. So what is our approach to solving this offloading problem? We designed a prediction-based algorithm for online assignment of mobile applications to cloudlets called OAMC. And OAMC assigns every application to a cloudlet at each time slot such that it leads to a low turnaround time during the application lifetime. So OAMC receives W and gamma as inputs. W indicates the number of feature time slot that will be used for offloading decisions. Also, OAMC uses the notion of gamma to reduce the impact of later time slots and decrease prediction inaccuracy. So U had and R had maintained a history of application and history of assignments. And then function predict based on the size of the window and the history of specifications predicts next W specification for applications. Then based on that, the cost of assigning applications to cloudlets is estimated. Our approach utilizes another function called assign to assign all applications to cloudlets. I will discuss more about functions predict and assign in next slides. So as I said, we have function predict. Function predict uses two forecasting methods. The if method, which is used to predict feature values of coordinates, and weighting moving average method, which is used to predict other specifications. So what are these methods and how they can work? In the drift method, the amount of change compared to the last observation depends on the average change in the historical data. However, weight moving average method gives more value to the latest observations. So the predictive value more likely to be close to the last observations. We believe Since users are constantly moving in a direction, drift method is more applicable for them. However, weighted moving average method is more applicable for other specifications, since applications are more likely to have same requirements over time. So this is our predict function. So we use drift method to calculate the feature values of coordinate x. We use weighted moving average method to calculate the feature values of intermediate data. Similarly, we use drift method to calculate the coordinate y, and weighted moving average method to calculate the feature values of other specifications. Okay. Let's continue to talk about assign function. This function needs to solve an instance of generalized assignment problem, which is a well-known NP-hard problem. And approximate algorithms have been proposed to solve this problem. However, they mostly require exponential pre-processing time, and they are complicated rounding techniques. In this paper, assign function uses the local ratio technique and to provide 2 plus epsilon approximate, so which has better running time. So let's continue to talk about experimental evaluation section. So we compare our algorithm, our approach with IP integer programming model, which acts as our benchmark. Another comparison approach is best fit decreasing or BFT approach. And another approach is our own algorithm without using prediction. We want to show the importance of prediction in our model. So to model applications specifications, for coordinates, we use mobility traces of taxi cabs in San Francisco. For processing speed, we use the performance metrics of 1,750 virtual machines managed by BitBrains. And for other specification, we use distribution, which is given in table 1 here. Similarly, for Cloudlets specifications, for coordinates, we randomly located Cloudlets within all possible positions of mobile applications. And for processing speed, we assume each cloudlet has the cumulative processing speed of 1 to 20 number of virtual machines. And for bandwidth, we use distribution here. These are our results. As you see, this result show our approach has a close to optimal turnaround time and much better turnaround time than other approaches, and above migration rate. Even though reducing migration rate is not our goal, but we believe approaches with lower migration rate can have better turnaround time. So we have much lower migration rate than other non-prediction based approaches. And IP lacks scalability, so it cannot solve problem for experiment 3, 4, and 5. And also above runtime, as we expected, IP has worse running time because of interactability of our NPR problem. BFT has the best running time because it is a fast and trivial algorithm. And our own algorithm has polynomially expansion over experiments and has better running time than OMC WP. To summarize, we discussed computation offloading can augment the capabilities of mobile devices, but it has a challenge due to uncertainties of mobile applications. We propose an approach called OMC to solve this challenge. For future work, we can work on efficient energy-aware offloading methods and while guaranteeing low turnaround time. We can also integrate the edge computing and 5G for providing ultra-low latency content delivery for users. That's all. Thank you for your attention.